I'm Steve Bates. This is Sean Gibb. I'm CTO at Adedicom as of less than a week, so there you go. I must know what I'm talking about then. And Sean's the VP of software. We're a startup based up in Calgary in the Great White North of Canada. A bunch of people who've worked on things like PCIe switching and RDMA and non-volatile memory and a whole bunch persistent memory, blah, blah, blah. And we've been working on a few kind of fun things, and me and Sean wanted to talk about those a little bit today. We've been doing an NVMe-based offload engine, so we kind of had this premise that people want to talk to accelerators. There's lots of different ways of doing it. Maybe NVMe is an interesting way of doing that. So that was a premise that actually ended up turning into something that we're now productizing, and I'm going to talk a little about why we are doing that, and Sean's going to talk about some of the specifics of what it is we're working on, and then I'm going to finish off by talking a little about some of the future directions that we're thinking of taking some of this work. So what we're doing is looking at acceleration right now, particularly for storage, though I think what we're working on could morph into something that's a little more general than just storage acceleration. So there's certain functions that you want to do in storage again and again and again. RAID for erasure coding or something like that is an obvious one. You want to protect the data. Somebody's probably paying you to store that data, and they probably want it back in its entirety at some point in the future. So putting some kind of parity on it, so if parts of it go missing, you can still get their data back, is a good thing. Deduplication is good for cost savings if the data isn't too entropic. And there's a lot of other things that you can do there. Like I said, most of us have NVMe somewhere in our background, and so we thought NVMe was an interesting one. It's already a storage protocol, so it ties nicely into storage acceleration. And we thought, well, how do we abuse, and I know Peter Anufric and Amber who work on the standards organization, and I think there's a few other people here too. I say we're using NVMe, but they might beat me up and say I'm abusing it, but whatever. So we were looking at what we're doing there. And then we're going to dig a little into the internals of what it is that we're working on with an embedded NVMe controller, talk about performance, and then I want to dig into some of the future stuff and on something that I've worked on quite a bit over the years, the last couple of years, is PCIe endpoint DMAs directly to each other, what we call peer-to-peer. So the ability for NVMe drives to pass information still under operating system control. So the operating system is still issuing the commands, but the actual DMAs are perhaps staying in the PCIe subsystem, perhaps underneath a PCIe switch or a switch fabric if there's one in there. And we've tied that into things like RDMA NICs and GPGPUs. And I actually have another talk specifically on that topic on Thursday. So blatant plug, come to the talk on Thursday. And you'll see lots and lots and lots on P2P mem, as we call it. But we can actually, as a NVMe engine, we can take advantage of that. We are a PCIe endpoint, like lots of other PCIe endpoints. And we also, one of the things we've done is focused on controller memory buffers, which is it's not that new of an NVMe feature, but we don't see it in too many NVMe drives yet, though we're starting to see it appear, and I'll talk a little about that. So acceleration, why do you want to do acceleration? Why not just do everything on those big beefy Xeon processors that most of us have? Well, as much as I love giving Intel money hand over fist all the time, every once in a while, maybe it's good to think about whether it's right to do certain acceleration functions on a Xeon or whether it's right to do it somewhere else, right? And we have a couple of friends from Mellanox in the room, right? People are putting offload engines in all kinds of PCIe endpoints. We see them in RDMA NICs. We are using graphic cards to do certain types of offload. Even NVMe drives, there's a couple of companies now that are offering additional services in those NVMe drives in addition to just storing your data, right? So people are looking at offloading the processors. And it's not just because Moore's law is coming to an end. It's because the I/O requirements of these endpoints is growing faster than the ability for the processor complex to absorb all those I/O. So in a standard DMA kind of framework, the system memory in a processor system has to bounce buffer every single piece of I/O. So every RDMA input, every NVMe output, every graphic card command, it's all got to get buffered in system memory, even though potentially the CPU doesn't even need to touch that data, right? And so moving it directly between the PCIe endpoints seems to make a lot of sense. And being able to do some of data manipulation in a PCIe endpoint, or a CCIX endpoint, or an OpenCAPI endpoint, or whatever. Doing it away from the Xeon cores can also make some sense in certain cases. The other thing is, of course, the noisy neighbor problem. The noisy neighbor problem is when a CPU is trying to do some pretty high revenue generating complicated computation on some data that's in system memory, right? So maybe you're doing fintech, or maybe you're doing biomedical imaging or something, but somebody is paying that Xeon core a lot of money to do that particular piece of processing. In the meantime, all your NVMe drives and all your RDMA NICs and all your standard NICs are DMAing to the same system memory that those CPU processor cores are trying to do load stores on. And I can guarantee you the quality of service that those load stores are getting under the influence of a lot of DMA traffic is worse than if the DMA traffic was not there, right? So that's called the noisy neighbor problem. The fact that this core is trying to do some work and it's being corrupted or polluted or maligned by all the DMA traffic going on in the system, right? Doesn't come for free. FPGAs can provide compelling solutions because they are flexible. We can do interesting things like I can do algorithm A at time A, and I can do algorithm B at time A plus delta, right? Partial reconfiguration will actually allow me to maintain my PCIe endpoint status. I don't have to bring the link down as a PCIe device. And I can actually change from an erasure coding device to a compression device to a dedupe device to a machine learning device to whatever. I can even have it so that the driver can do partial reconfiguration with bit files that I, as an endpoint, don't even need to know about. So if someone wants to do something proprietary or confidential, there's ways of letting them do that. So the device that we put together is codenamed NoLoad. Well, it's not codenamed. It's actually, the product name is NoLoad, which stands for NVMe Offload. So what is it we're doing? Well, we're not a huge company, so we're not a hardware company. We're focusing on doing essentially bit files for FPGAs initially, and those come in a range of form factors. And like I said, our key hypothesis is that NVMe is an interesting interface. So the great thing is, once you assume that, you get to play in the wonderful world of NVMe, which is a really rapidly growing world right now. So I'm going to stop talking to the mic. But anywhere you see an NVMe SSD today, we can exist, right? So I can go to Alpha Data or Nalitech or somebody else and buy an FPGA card, and I can put my bit file on that card and plug it into a server, and it's an NVMe device. The driver will bind to it, applications will treat it like a device. I can do a 2.5 inch. There are some people already doing this, FPGAs in 2.5 inch U.2 form factor, SFF 8639 connector. I could go to Supermicro and buy a 2U with 20 bays front loaded, populated with these, and I've suddenly got an FPGA acceleration monster. But it's still all NVMe. Amazon recently, well not that recently, a couple of months ago announced AWS F1 instances enabled with Xilinx FPGAs. They have an API. We can implement our bit file for that. And then we can either build services on top of that, or people can rent our bit file and pay Amazon a certain amount of money per minute, and we get a share of that. So that's the go-to-market strategy. So why NVMe? Well, if we look at what an accelerator needs in terms of a transfer protocol, there's quite a few things that come through. Low latency, we need that for high performance, right? If we're going to go away from the CPU, we kind of need to be able to do things quickly. High throughput, low CPU utilization, so we'd like not to be taxing the CPU while we're using the accelerator. Ideally, something that scales well in a multi-core environment. We're going to be sitting in large servers that probably have quite a few cores in there. Those cores may not be Intel, it might be ARM, it might be PowerPC or PPC. And have some sense of QoS and awareness. Now, if you look at what NVMe is defined around, the reason why NVMe was designed, and I'm on the panel tonight around NVMe, and you can come and hear me sing about NVMe. So look forward to that, yes. But some of the things that actually were fundamental to why we wrote the standard for NVMe were low latency, high throughput, low CPU overhead. Those were the key idioms in our heads. Well, not in my head, a little before my time, but in the heads of the people when we first started writing the NVMe spec. Multi-core awareness was very important for NVMe, and QoS awareness is probably like the word that defines what NVMe is now working on in terms of streams and directives and priority queuing and so forth. So all of those things are important to NVMe, and they're important to a good accelerator. So the question isn't really why use something, why use NVMe? It's almost like, why would you use anything else, right? There's certain things that you just get there. In addition to that, by using NVMe, we get to take advantage of the entire NVMe ecosystem. So I have 40 or 50 of the world's best Linux kernel hackers writing the driver for me, because I'm using the NVMe driver. I get NVMe CLI for free. I get NVMe Over Fabrics for free. Now I can share my accelerators across networks. That's pretty cool. Anyway, so acceleration over NVMe allows us to basically move data using DMAs, right? NVMe is really just a DMA request command, completion kind of protocol. So we don't need a proprietary driver. That's great, because I hate writing drivers. So I don't have to do that. And also the driver for NVMe and Linux and other operating systems is very good. We can plug, and we have already done this, we can plug our no-load into an ARM box. We can plug it into a Power. We can plug it into an Intel. If it's running Linux, it just comes up as an NVMe drive. If it's running Windows, it just comes up as an NVMe drive. If it's running VMware, it just comes up as an NVMe drive. All the wonderful things that people have been doing to make NVMe so ubiquitous are something that we can leverage, right? We get to use all the standard tools. We use FIO for testing. We use NVMe CLI for management. All of that comes for free. We don't have to write our own benchmarks. We've got a great software and ecosystem. I talked about the ecosystem a little earlier. New ISIS outside have a couple of examples of small storage servers and JBOFs. Again, we can put or our customers can put devices in there, and we can tie into fabrics. And like I said, yeah, very interesting, we can tie into the network. So that's kind of the rationale, and we can argue over beer whether it's a good rationale or not, as long as you're buying the beer. But before, I'm going to step over to Sean now, who's going to walk into some of the more detailed specifics of the internals of what we've been working on, and then I'll jump in at the end for some of the future direction stuff. So, Sean.
All right. So here we have a basic architecture of what a no-load card might look like, an accelerator card might look like. I'm going to talk without the mic too a bit so I can point over here. So we have a host CPU that talks through PCIe, either directly connected or through a PCI switch, to an FPGA board. That FPGA board has onboard DDR and an FPGA. This card will present as an NVMe 1.3 device. So when we plug the card in, we boot up in Linux or Windows, it presents as an NVMe 1.3 device. And inside of that NVMe device, we've partitioned out accelerators and mapped them one-to-one to namespaces. So if you have an accelerator function, for instance, an EC accelerator, that would present as a namespace. Maybe you have a dedupe accelerator, that will present as a different namespace. So if you have 5 accelerators, you'll have 5 NVMe namespaces that are presented with this card. The host CPU will communicate with the card, just like it would with an NVMe drive. So it'll send NVMe commands over the PCIe bus. We'll grab them, just using the standard protocol that you would use with an SSD. I don't want to spend too much time on this, but I want to just point out the CMB here. We use one of the things we use the external DDR for is to put a controller memory buffer in. That allows us to do some interesting things that Stephen's going to talk a little bit about at the end. We also use it we've also used it quite a bit to test our NVMe controller, and I'll show the performance results from that a little bit later. But we present ourselves as a RAM drive, so to speak, an NVMe RAM drive, which allows us to performance test our controller. So this is just a little screenshot of an NVMe CLI list, just to show that we present as just another standard NVMe drive. At this point, we are 1.2. Yes, this is in fact a 281 terabyte drive, it looks like. We did that with a little bit of LFSR that we won't talk about much, but
that's the cheapest drive you're ever going to get. $256. I'll explain in the pod why we did that one.
So, now that I've kind of defined that accelerators present as namespaces, it's probably a natural step to say, okay, well, the identify namespace command in the NVMe spec allows us to do accelerator discovery. So if we know that there's an accelerator there, we can do it, or we know there's a namespace there, we can do accelerator discovery on that by issuing an identify namespace command. And in addition to filling out all of the standard mandatory fields in the identify namespace command, we have the vendor-specific section of it that we utilize. And some of the stuff we put in there is basically things that are specific to that accelerator. So the first few fields, we've decided to make SDXL compatible. So it's laid out exactly like Xilinx's SDXL register interface. And then after that, we put the accelerator name, things like the accelerator name, the version number, and then anything specific to that accelerator. So the kind of information that a user of the acceleration function might want access to in a read-only kind of basis. So I want to know, perhaps the state of some internal registers, or I want to know, some more specifics about how that accelerator is configured. So that kind of information can be put in there. We built an interface specification that allows for partial reconfigurability, and again, by using the NVMe infrastructure, we're able to introduce new namespaces so that those accelerators can be discovered and talked to. And on top of that, we built a host API. It's a very thin API that really just wraps up a lot of the built-in functions in the operating system to make it easy to talk to and discover accelerators. Okay. So once we've kind of discovered this accelerator, it will be important to be able to, it's important to be able to configure it in many accelerator cases. So what are the ways that we can do that? Well, there's two different ways. First off, we can use vendor-specific commands. And what vendor-specific commands allow us to do is we've gone and added our own vendor-specific command and used 190, that allows us, overloading that command allows us to provide 192 bits of configuration via a single command into the accelerator. It'll just go through the normal command queues. It's up to the accelerator how to use that. At the controller level, we're just a transport protocol to get config and data in and out of the accelerator. So it's up to the accelerator to do that. But in some cases, we've built acceleration functions that require quite a bit more than 192 bits of configuration. So how did we deal with that? Well, in that case, we mapped a certain LBA range in the accelerator, in the namespace, to be configuration. So, for instance, with the EC accelerator we're going to talk about a little bit later, we mapped a region, LBA region, to hold the configuration required to set up the EC. And just by writing to that offset, using a simple file handle, it's possible to configure that accelerator with the information it has. So, data management. Now that we've got the accelerator, we know all about it, we've got a file handle to it because of the identify namespace discovery, we've configured it, how do we get data in and out? Well, it's pretty easy. Really, data is transferred to a specific accelerator by performing an NVMe write to that accelerator. And then data is pulled from a specific, results are pulled from a specific accelerator by performing an NVMe read from that accelerator. And that's really what it boils down to. It's very easy to get the data in and out of the accelerator because we're just performing NVMe reads and writes. And at the host level, that just looks like file handle operations. Very simple. As I mentioned before, for configuration, we can use LBA offsets to represent different areas of the accelerator. So, for instance, if I was doing a RAID-style EC, I might map different regions to different disks. So then I can write in the data from those different disks into the different regions, tell it to proceed with the acceleration, and then pull the data either from specifically mapped LBAs. And one other just little side note is because NVMe has the format command, it's very easy to vary the block size for the accelerator. So, for instance, maybe the accelerator, we want to pass in 4K blocks for one function and 8K blocks for a different function. This allows us, the format command makes it easy to do that. Okay, so now to switch gears a little bit. So this is kind of maybe a little bit of the details of how we how we use NVMe to perform acceleration, we went and built our controller. We decided we'd use an embedded processor for the controller. And the reason we did that, first off, as Stephen mentioned, we're a small company, but the real reason is that an embedded controller, because it's software, has a lot of flexibility for us. And one thing that we've been able to do because we have a software controller is we had a very fast turnaround time on compliance testing and debugging. So on bringing it up as an NVMe device, it was very easy when we plugged in the card, easy in relative terms, when we plugged in the card and the BIOS crashed and didn't recognize it, to go quickly turn around ideas to get past the BIOS, and then to get through the operating system's drivers. Second thing that we've been able to do is we've been able to quickly implement new NVMe features. CMB is one of the features. It took us about 1 day to put CMB in because we have a software controller. We have NVMe SGLN, no drivers to test it with presently, but it only took about a day to put it in because it's a software controller. So having that software controller made it very flexible. The downside, of course, with any software, embedded system software would be versus a custom RTL solution would be squeezing performance out of it is going to take more work. And to do that, we've had to write coprocessors or offload engines to assist us. So, what processor were we going to use? Well, we had a couple of hard requirements. The first thing we really wanted was to be platform agnostic. And by platform agnostic, I mean we didn't want to be tied to Xilinx or Altera or Microsemi for an FPGA. We didn't even want to be tied to FPGAs necessarily. It would be nice if the processor could also work on an ASIC. So we needed to be platform agnostic. Second thing we wanted for that processor is broad software ecosystem. So even though we're not using Linux on it, for instance, it would be nice if that processor had a Linux distribution that we could put on it. It would be, we wanted to be able to use standard compilers like GCC or LVM. We didn't want to be tied down to one specific compiler. And then we had a couple of soft requirements that were nice to have, an extensible instruction set, and both 32 and 64-bit addressing, but those were not necessarily showstoppers. So what processor did we use? We chose to use RISC-V. So for those who don't know, RISC-V is an instruction set architecture that was developed at Berkeley in 2010, and it's gaining some momentum in academia and industry. I read recently about that NVIDIA has chosen to use the RISC-V instruction set architecture to build a homebrewed, an internally built RISC-V processor to replace their Falcon processor. So it's gaining a little bit of momentum. There is commercial implementations of the ISA available. There's also some open source ones, and including the ability to auto-generate an open source core from it. And the final point is that it met all of our hard requirements and our soft requirements with a few caveats, which I'll discuss. So, in terms of getting a RISC-V core, the first option we looked at is to use the Rocket Core generator. That's directly from the RISC-V organization. And we went and took the RTL that came out of that, tried to build it to an FPGA. We only got 50 megahertz on an ultra-scale FPGA because Rocket Core generator is really suited towards ASIC implementation. So we had to quickly throw that idea out and look for another idea. And we turned up a core called Orca, which is an implementation of the instruction set architecture that's BSD licensed and FPGA optimized. It has a 32-bit addressing solution, and we were able to, with our very first compile, achieve 125 megahertz. So we use that as our starting point to build up our own RISC-V core. So just a little aside about RISC-V in terms of the ecosystem. It does include support for GCC with GDB, although, as I'm going to mention a little bit later, the GDB support is not entirely helpful in an embedded system. It has an LLVM toolchain. They have their own simulator called Spike, and there is a QEMU model of it. And then, like I said, there is support for different operating Linux-based or BSD-based operating systems. Okay, so our development process to get our controller up and running. First thing was we sat down and wrote it in C. And then we took the QEMU NVMe branch and plugged our controller in, replaced the controller that was there with our controller, and kind of were able to test and bring up the main functionality of it. So, we were able to work out all the little kinks like, do I have my bits aiming the right direction? Am I packing and unpacking the bits from the right places? Is my main controller loop working? We kind of got through all those, but there was a couple of complications in the QEMU NVMe branch where we had to fake PRPs and fake the DMA. And as a result of that, of course, when we went to put it on the RISC-V, we discovered that the PRP implementation we had was botched, so we had to debug that. And of course, we had to write our own DMAs. So we kind of got through that process in QEMU, ported it, and then after debugging it, got it up and running in both Linux and Windows by using that DDR on the board to build an NVMe RAM drive, which we could write things to. We could format, write to, read from, reboot, write in Linux, reboot in Windows, just make sure that it was working like a drive, and then perform some performance testing on that RAM drive to characterize the behavior of our NVMe controller. So I'm not going to spend too much time on the test setup, but for the test setup for the curves I'm going to show here, we have a couple of different FPGA boards we're working with, an Alitech and an Alpha Data card. Both of them, one of them is PCIe Gen 3 by 16 capable or 4 by 8, and one is Gen 3 by 8. They both have RAM on them, and then we use a Viavi PCIe capture card to verify all our results that we're seeing. So we went and took that, plugged the card in the very first time, let's say, after we kind of got it debugged. It comes up as a drive, and we were pretty underwhelmed by the first results we got from FIO. So as Stephen mentioned, because because it appears like NVMe, we're able to use all the built-in tools that are available in the NVMe ecosystem. So we used FIO, and as you can see, we're only getting on a Gen 3 by 8, where we should be getting closer to 7 gig, we're getting 2.5 gig on big blocks and like 80 meg or something on small blocks. So we were excited that it was coming up as a drive, but underwhelmed by the results, because we weren't even capable with 4 meg transfers of saturating the bus. Now, it's NVMe, so recall it's a block-based transfer protocol. So a 4 meg transfer is really made up of about 1,000 4K transfers. But even with that, we weren't able to keep the DMA engine busy all the time. So our first concern was, how do we get that DMA engine speed up? How do we keep it, first off, is our DMA engine capable of getting to 7 gig, and are we able to keep it fed? So we built a test that would allow us to verify that that was the case. And there was a few things that we realized as we went through. First off, the Orca implementation had a few bugs in it that were causing troubles. We had to debug those and kind of patch those in. There were some instruction bubbles in the processor, so we had to change the architecture of the processor a little bit to remove the instruction bubbles. And then, through manipulations on the core, we were able to get the compile speed up to about 250 megahertz on an UltraScale Plus, or 190 megahertz on an UltraScale FPGA. So, if you count for that, that approximately doubles our performance, which gets us to about 5 gigabytes per second, which is still not saturating the bus. So, as we went through the testing process, we realized, and we kind of knew this beforehand that this would happen, but we had tangible evidence that we would need to build a coprocessor to offload the data transfers and the completion commands, so that we could the RISC-V could do the parsing on the commands and decisions on the commands, but then fire it off to this coprocessor that could then go and work with it while the RISC-V core started working on the next command. And this is kind of where we're at now. So first, a little discussion. This blue line was the line that was underwhelming on 2 slides ago. This yellow line was a test that we did where we used the PCIe IP, the DMA that we have, and the RISC-V as a little test just to see, can we pump enough data through, and where is our bottlenecks in the system. And initially, in the early test, this was not up here at 7, it was down at 4. And through improvements, we were able to get that little ecosystem where it tests those 3 IP blocks up to saturating the PCIe bus for 2K blocks and larger. So another thing we can see here is that the reads and writes, they're about the same on this RAM drive, not unexpectedly. We're able to saturate the bus for 128 kilobyte transfers and larger, currently with the current system. So in order to improve the throughput of the system for small blocks, we're going to have to put on multiple RISC-V cores so that we can perform more command processing in parallel. But right now, for 4K cores, we're getting about a gigabyte per second. Latency. So the latency here, this is a little bit, this slide was different a week ago. We've improved the results quite a bit. But the latency we're getting for small transfers is about 12 microseconds. And then, of course, as the transfer size goes up, the DMA time starts to take more and more time on the latency. These latency results are from FIO. So as the size goes up, more and more of the time is dedicated to the DMA transfer time. But what you can see is that we're getting about 12 microseconds on a 4K block. One side note is that acceleration over NVMe will tend to focus on throughput more than latency. So because you're doing big transfers into and out of it, because it's a PCIe DMA-based acceleration engine, you're going to want to transfer large chunks of data in and out. So throughput is going to matter, is going to be the focus more than the latency. That said, our goal is still to get our latency below 10 microseconds, and we have a pretty good path to get there. So just a little side note of complications with the RISC-V. First thing is, there is a GDB debugger, but there's no external debugger for RISC-V yet. So there's no JTAG debugger, there's no capability of getting right into the heart of the processor from an external system. So for an embedded system, there were some complications with debugging. We had to build our own internal debugger to make it possible to track down the bugs in the system. We turned up, as I mentioned before, several bugs in Orca that we had to fix. And there's a few underbaked features in the Orca implementation, especially revolving around interrupts that have caused us to architect the design in a particular way that avoids interrupts as much as possible. So now to shift gears for a quick little discussion about a case study we did. We decided that we were going to take ISAL and do an ISAL-compatible Reed-Solomon EC accelerator for 32-port. And we built one that utilizes 16 kilobyte blocks. And with that, we were able to saturate the PCIe Gen 3x8 throughput, so get 8 gigabytes per second. And once we had the little piece of RTL required to do the EC, we went and modified the ISAL perf test. Took us about 45 minutes to modify it, get it up and running, and test it. So because of the whole ecosystem of having the NVMe here and having the very simple interface to the NVMe, it took us very little time to put this accelerator in and get it tested. It took us about 10 lines of code to get it in. So, we were pretty happy with how easy it was to integrate that in and get it tested and know it was working. And our roadmap includes, just as a side note, dual namespace version that's capable of 16 gigabytes per second. So I'm going to turn the time back over to Stephen for a change in gears to go back to talking about controller memory buffer.
Doing a little bit of shimmying back and forth. Thanks, Sean. So I think maybe just on that previous slide, basically, because we're doing NVMe, we get advantage of standard system calls, read, write, p-read, p-write, pv-read, to, anything that's going to have anything to do with block-based semantics, we can take advantage of. An ISAL, which is a storage-based library mainly from Intel, it's working for storage-type data, so throughput and large block sizes are pretty common. So that was a very easy one to tie into. And that's one of the reasons why storage acceleration is our primary focus right now, though we're obviously looking at other application spaces. But it was really very easy to tie that in. And like Sean said, because the block sizes were larger, we hit that upper limit of the PCIe bottleneck, 8 lanes of Gen 3. And We do have some cards that are going to be 8 lanes of Gen 4, right? We're FPGA-based. FPGAs tend to be on the cutting edge of I/O. So we have already got PCIe Gen 4 cards in our lab. We just need other Gen 4 things to connect them to. And I see a few people in here who work for companies that have Gen 4 already in certain things. So, these are the kinds of people we want to work with. And then parallelizing it so that we can get to 16 gigabytes in a single card, or parallelizing across multiple devices behind a switch is also possible. Of course, there's competition, right? We have other ways of doing offload, so we have to be cognizant of that as well. But I want to jump gears. As Sean mentioned, we based around a RISC-V. That was great from a flexibility and getting things in very quickly. One of the things that was really important to me from very early on was controller memory buffers. So controller memory buffers are part of the NVMe standard, and they have been for a while. And basically, it is a PCIe bar. So it's just a region of memory that's I/O memory that lives on the NVMe device, and you can do basically memory reads and memory writes to those locations, right? It's not system memory. It's not coherent. Well, certainly not an Intel architecture, it's not. But it is memory that can be written to and can be the destination and source for DMAs from other devices in the system. So if I have a DMA engine, and every single NVMe drive on the planet has a DMA engine, then it can use its DMA engine to write data to or read data from a CMB that's anywhere within its visibility domain, which typically in PCIe is pretty much everywhere. But again, that depends a little bit. And having worked with PCIe switches, it's an area we know pretty well. So CMBs are standardized. We implemented one. A lot of drives, well, not a lot, but I'm starting to see some drives in the market that support CMB. So Intel have started shipping one on their dual port. I think some of the other vendors are starting to ship them. But CMBs can support different types of features. So in the standard, it says you can have a CMB, and then there's one hot encoding for what it supports. It can support submission queues and or completion queues and or PRP lists and or write data and or read data. And most of the drives I've seen so far only support submission queues. And the upstreamed Linux driver today only enables submission queues. So if you use inbox Linux, you can't use anything else. But I don't know Linux very well, looking at a few people in here who know Linux very well, but even I know enough to hack it to get other things to work. So that's what I did. So we aren't really using and I'm going to talk about this more in Thursday's talk. I'm not so interested in CMBs for local access from the local CPU. I'm looking at this more from other PCIe endpoints being able to talk to me, and I being able to talk to them as a PCIe endpoint myself, right? So now I'm the no-load. I have a CMB. People can DMA to me and pass me data and messages, and I can basically put stuff in my CMB and maybe get the OS to do a DMA, or get the OS to issue a DMA request to the other device so it sucks data out of me. So we can do all that kind of stuff. Or if they have a CMB, I can DMA to them. But we did think it would be interesting to test some of the CMB functionality. So what we did is we actually ran some FIO tests, and we did it with the standard upstream kind of Linux NVMe driver. And we did it with the submission queues in host memory and the submission queues in the memory on the drive. So this is kind of what Intel are now starting to support, and I think what some of the other vendors are. And interestingly, and to be honest, I haven't looked at the PCIe analyzer in detail. We just got these results quite recently. But interestingly, we saw that the latency was better when the submission queues were in the CMB. And there's a couple of reasons why you can argue that seems reasonable. And we also saw that the throughput was better until we reached the saturation point of PCIe. Now, not hugely better, but it was definitely a little bit better. And some of that's to do with whether it's better if the CPU pushes the data down to us or whether we DMA it from them and blah, blah, blah. And this is just the submission queue entries. This is not the actual read and write data. That's still, at least in this test, doing standard flows. So it's great that it works, and it's pretty interesting. But like I said, this is not the most interesting thing about CMB for me. This is the most interesting, or one of the most interesting things about the CMB for me. So a couple of use cases. I don't have performance data on this because you'll see it on Thursday. So come to Thursday's talk if you want to see the performance data, or buy me a drink and I'll show you the slides. But what we wanted to do, or what we're really trying to do now is, because we've got no load, and like Sean said, we're working daily to improve the performance of no load, and it's going to get better. We're going to continue to get that performance up, the latency down, more features in. But given that we have this as a starting point, part of my role is to look at how do we take this building block, this no-load accelerator, and do really cool things with it. And so one of the things we can do is, because it's a CMB, we can use it really simply as a bounce buffer. So here's an example where I have basically two standard NVMe drives. These could be M.2s or U.2s or whatever. And I have the Adedicom no-load as another NVMe device, but this one has a CMB. And what I can do is, and I'm going to come away from here, the CPU can say, do a DMA and put the data in the CMB here. The address in the PRP that's sent to this drive doesn't have to be a system memory address. It's a physical address. It can be anywhere that's addressable. That includes the CMB on here. This DMA engine will happily do that. There's no, it doesn't do any checks. It's just an endpoint. The OS might do some checks. You can hack the kernel to get around it. Or maybe we'll upstream something. I'm hoping we will. We'll see. The data lands here, and then this guy can issue a DMA, an NVMe command saying, take the data, or DMA in data from this address, and put it somewhere in your NAND, or your Optane, or your spin-torque MRAM, or your accelerator, or your whatever, right? Or your RDMA, or your network, right? It doesn't care. It's going to do a DMA, pull in data, encapsulate it in something, and do something with it, or send it somewhere, or store it somewhere, whatever, right? This guy really isn't doing that much. He's just a bounce buffer. So that's model number one. But still interesting, okay? And in this case, there's two external DMAs, right? The NVMe drive A DMAs it to somewhere. NVMe drive B sucks it in from somewhere. If the other model is when we treat this as a true CMB, okay? And in that case, what happens is the CPU issues a command here. He'll DMA it into the CMB. The OS issues a command to us and says, please take the data that's in your CMB, or it sends us an NVMe command, and what happens is we know where our CMB is, and we look at the PRP, and we go, this PRP is not external to us, this PRP is in our bar. The BIOS enumeration tells us this. And so we know the data is in our bar, we suck it via internal DMA, and we put it wherever. We put it in our erasure coding accelerator, we could maybe put it in our dedupe accelerator. If we had a network interface off the back of us, we could put it into packets and send it out on the network. If we had a printer connected to the back of us, we could take that data and print it out as a dot matrix. Right? We could do anything with it. This doesn't have to be an NVMe drive. This could be an RDMA NIC. This could be a TCP/IP NIC, which is a little more complicated because there'll be headers and footers. We might have to do something funky there, but it could be that. Right? But now we have PCIe endpoints that can move data around. Assuming we're doing some interesting kind of data manipulation, data gets filled to us, we generate erasure coding parity, we push it to an RDMA NIC, the RDMA NIC sends it out of the network. We're now doing erasure coding at scale. Right? Or there's a whole bunch of NVMe drives. We're a storage array. And basically the CPU can lazily copy data to us, we dedupe it, and then we find all the dedupe matches, and we tell the OS, you can trim that stuff. And that all happens in the background. And none of the traffic is going to the CPU. If there's a PCIe switch in there, none of the traffic is even touching the CPU. Right? It stays beneath the PCIe switch. Right? These are just a couple of use cases. There's many, many more. And depending on what kind of accelerator you put in the Adedicom no-load, you can do all kinds of stuff. Like I said, it doesn't even have to be accelerators we know. Partial reconfiguration and an API would allow people to download any accelerator they liked as long as it fits. So we do have performance data on CMB, and some of that will show up on Thursday. Obviously, if you're interested, you can get in touch and talk to us, and under NDA we can share lots more and where we're going and how we're going to tie this to fabrics and how the world is going to be a better place. But that today we kind of give you an interesting starting point to take a look at it. In summary, it's an NVMe compliant FPGA accelerator. Right? That's what we're doing. We're targeting various form factors, PCIe card, U.2, so we can plug it into storage servers, and cloud-based images like AWS F1 or Baidu, or even this week, I think Huawei announced they're doing FPGA-enabled instances in the cloud with Xilinx. We have already got support for certain NVMe features like scatter-gather lists, controller memory buffers, SOIOV, which is great for virtualization, and there's some fun things we're going to do in that space. Coming soon, more accelerators. We're going to do some ourselves. Some partners are going to work with us to do some, and we're going to enable people to be able to push their own down to us via the create namespace command. Improved performance, including PCIe Gen 4. Right, we're using FPGAs that are already Gen 4 enabled. We just need Gen 4 things to talk to. And obviously, NVMe Over Fabrics is really exciting because we are NVMe namespaces. NVMe Over Fabrics is all about exporting those namespaces over a transport. Why not export an accelerator rather than exporting storage? So that's where we're going. Thanks for your time. And if you have any questions for me and Sean, I think we have a few minutes. Otherwise, I'll see you in the bar.
So on the CMB, right, you try that now under congested conditions with the PCIe switch?
Yep. It works fine. Yeah.
You see better results with congestion?
I can set it up so that I can have a whole ton of traffic going up to the host processor, and I can move data between two endpoints that are in another section of the switch, and they're completely unaffected. So I can have I could have an RDMA NIC pushing data full speed to the DRAM on the CPU, and in another partition or another VP of the switch, I can have the NVMe drives and the Adedicom talking to each other, and they're all working max capacity, right? These switches are non-blocking. I mean, they'll take a lot of capacity, a lot of throughput.
You try that with the control traffic?
Yep. Yep. The control traffic is such a small percentage of the overall, and it has, it's such a small, even if it gets slowed down a little bit, it doesn't affect the performance. Maybe at Q depth 1, you'd start to see some problems, but if you're doing a lot of throughput with a high Q depth and maybe a lot of threads running, like we don't see a noticeable drop in throughput, especially with PRP lists, and SGLs would be even better. So if someone I think there was somebody trying to get SGL support into the driver. I see Martin nodding his head. I saw that the other week. So SGLs would be even better because then the overhead per command to data transfer goes down for large transfers because now it's a scatter-gather list rather than a PRP list. Yeah. So I think we have serious advantages in terms of maximizing how much traffic is throwing through your system at any given point in time, because we are not all the traffic is going through the upstream port anymore to the processor.
Well, second question. So what does the accelerator actually do? It complements the driver?
So the erasure coding one actually does exactly the same mathematical manipulation as ISAL. So you write a bunch of data, and our accelerator will calculate RAID parity, so it will do Reed-Solomon on the traffic as it comes in, and it will generate the resultant parity that is bitwise identical to what ISAL would have done on the processor or in the Lewisburg if you're using the crypto offload or whatever. And then when you read back from a specific LBA range, you get that parity. Right? So the idea is you basically write a whole bunch of LBAs, and that, as you're writing to us, we're not storing the data. We're mathematically processing it and generating a result that we store in DRAM. And then when you sometime later read back from a different LBA range, you get the results. So we are an offload engine, exactly. And dedupe would basically be write and 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 write. And we form basically a scatter-gather list of matching keys, like SHAs. And then you can read back and we tell you, this is what the matches were and this is where they're located. All right, so you could basically take an entire file system and copy it to us, and we'll just consume it. And the end result when you read it back is just pointers to where the matches are, so you can trim that data away because it's duplicate. Right. And so different accelerators will work slightly differently depending on what you want to do. So one of the ones you might have seen was the LFSR. So the LFSR is 256 TB of space, and basically it's just pseudo-random generated. So it's the seed, it's a generator polynomial based on the seed that's the LBA. So when you read from it, you get what seems random, but it's pseudo-random data. You can calculate what it's going to be. And then when you write to it, it basically tells you if there's a match or not. I actually find that accelerator is very useful for test purposes. And also, unlike NAND, you're not wearing a die. Sorry, Warren.
In the case where it's an accelerator that generates maybe the same amount of data as it gets in, maybe rate recording is not exactly,
Yep.
compression may be included in the future. So would you pipeline writes and reads just one
Yeah.
after the other on the sense of mixture? Does that provide you the guarantee that when you do the read, the data is ready?
Yeah, so you can take advantage of the same barriers that we have in the POSIX. I mean, POSIX compliance still holds because that's enforced by the OS. So if you want to be, to be honest, it's done on a per accelerator basis, and we spend, some time. If it's an accelerator that a specific customer wants, we'll work with them to map out the API or the interface that works best for them. But for anything that requires some kind of consistency, we just take advantage of the consistency rules in the system calls, the POSIX system calls that exist already. Right? So if you issue a write barrier, it means that anything that follows that write barrier is going to read what was previously written. And we can take advantage of that because the operating systems support it. Right? So you can do that. So we can have some of our accelerators are single-threaded internally. They can only accept writes on a certain range. Others, you can actually write multi-threaded and actually take the LBA space, divide it up. Some of the accelerators involve writing the same LBA over and over again, and others involve writing a huge range of LBAs. And to be honest, it really depends on what the accelerator is and how people want to use it. And we're still early days for us, so we're very interested in talking to end users and finding out what accelerators do you want and how would you like to talk to them. I don't claim to be able to have all the answers there, so it's definitely a discussion that we're super keen to have. Yeah.
Have you bolted like your EC accelerator into any storage system and taken any benchmarks versus something that's running?
So the ISAL is a benchmark, like it's a library from Intel with a performance benchmark. So we put it in there and we were getting 8 gigabytes per second with the FPGA. So the ISAL, with the Intel, depending on whether you use their offload engines, they can get more throughput. They can do like 11 or 12 gigabytes per second, but you're paying for that with Xeon cores and Lewisburg offload engines. So it becomes would you rather pay for the FPGA or would you rather pay for the other? And I don't think there's a single right answer to that. Some people, yeah. Yes, right now it's just micro. We'd love to put it into a storage system if you have one. All right, we're out of time. Thank you very much. Thank you, everyone.